Hi, GK, CRHS. Today, conservation of momentum. Most people know a statement of the conservation laws, whether it's momentum, energy, mass, whatever it happens to be. We say it can't be created or destroyed. The part that folks often leave out, though, is whatever it is we're talking about can be transferred between the objects. So where we can't get rid of momentum and we can't make momentum, we can move momentum around between different objects. And that's going to be the general thesis of our talk today. In your reference table, your PRT, the only equation they give you for momentum conservation is this. The P before equals P after. The momentum before some event is equal to the momentum after the event. And I know that doesn't seem like much, but that's the power of the conservation laws. What's missing is the during part. Let's say we have two objects that are coming together and they collide, and they could stick or they could bounce off, whatever that happens to be. During that interaction where they're actually hitting, things are changing very fast. And when we use momentum conservation, we don't have to worry about what's going on during the collision. All we need to know is what's the momentum before, and we can figure out the momentum after without sweating all the details about what's going on during. However, this means that we also have to write our own equation that says that momentum before whatever event it is that we're talking about is going to be equal to the momentum after that event. So we're not given the details here. We're going to have to come up with our own equations, and I'm going to show you some templates that you can use to work with. So there are three cases of momentum conservation that you have to work with in the Regents course. The first one is the elastic collision. If you recall, elastic collisions are bouncy collisions. Things hit and bounce off. And of course, we're going to apply the equation in the reference table, P before equals P after. But when we write our own equation, we can always use something like this. If we're dealing with two objects, the before side is over here. So we have mass 1, velocity 1 plus mass 2, velocity 2. What we're doing here is we're adding up the momentum of these objects before the collision. And that has to be equal to the momentum afterwards. Well, momentum is mv, so we have m1, v1, and then we're going to prime this over here because this object is going to be going at a different speed probably over here than it was going over here. So we have m1, v1 prime plus m2, v2 prime. So whenever you identify something as an elastic or a bouncy collision, this is the equation that you're going to write as the follow-up to P before equals P after. Let's say we have an inelastic collision, and that's where things hit and stick. So if we have an inelastic collision, we might have an object over here and something else hits it, and then they move off as one lump of material. So we have P before equals P after again, and this is the momentum of the objects before the collision, m1, v1 plus m2, v2. But what we have after the collision, these two objects are stuck together. So we have one object with the combined masses of the two, m1 plus m2. This is our stuck together object. And then we don't need a number over here. It's just moving along at some different speed that we'll call v prime. So inelastic collisions, you lump the masses together over on this side, and we can combine this. We only end up with one term really over here, but two terms over on the other side. And then we have our explosion problem. And I'll air quote when I say explosion, because it doesn't necessarily involve an explosion, but that's the classic example. Let's say we had a cannon here, or something like that. Before the cannon is fired, it's just sitting there. It's got mass, but it doesn't have any velocity, so its momentum is 0. And the explosion problem is one in which the initial momentum is 0. Now, this is just a separator. This is during. And then afterwards, the cannon fires the projectile. Well, the projectile goes one way, the cannon goes the other way. Momentum is a vector. So this has positive momentum. This one has negative momentum. And those are going to add up to 0, which is the momentum that we started out with. So it's not that we can't make momentum in the sense that we can't create motion. We can make momentum, but because the momentum vectors are equal and opposite, it's just like Newton 3, they're going to cancel out. So we're starting off here by saying the momentum before the collision or the event is the same as the momentum after, but in the explosion problem, the initial momentum is 0. So we have 0 is equal to m1 v1 prime plus m2 v2 prime. In class, we're going to start out, I'll take you through an example of each one of these problems and show you how we can solve them numerically.